In this video, we're going to take a look at different ways that we represent different types of data, both in math classes and in real life. We'll take a look at a number of different ones and the purposes of what they're used for. I'm assuming that you know what these are to begin with. I'm just going to walk you through them very quickly and also focus on the purposes for each one. One type of graph is just a bar graph, where you're going to have the bars representing the data for each category. Now, the categories don't have to be numerical. You could have them being your favorite ice cream flavors. They could be animals that people have as pets. They also could be numbers. They could be an age group, for example, but they don't have to be. With these, the taller the bar, the more answers there are, the more data there is in that specific category. A histogram is a special kind of bar graph. It looks exactly like a bar graph, except it's always numerical, and the data has to have groups of numbers with common intervals. So, for example, if you're doing, let's say, data for certain age groups, you'd have to group people by ages maybe in 3s or 4s or 10s, but it has to be common. So you might say, well, we'll look at people from 1 to 5, and then you have to say 6 to 10, 11 to 15, etc. And the idea is going to be that as you're setting these intervals up, it's always the same distance, the same number of numbers there. So see, we have 5 numbers. We also have 5 numbers here and 5 numbers here. It's easy to double check also, because when you go this way on your intervals, they always should be the same. So these are 5 apart, these are 5 apart, and the same on the left side. So if you go to 16 to 21, then here you have a problem, because when you've done that, we now have different spacing. On the left side, everything's okay, right? This is 5 and this is 5, but here this is 5, this is 6. We have too many numbers here, so you'd have to fix that and say it's 16 to 20. A picture graph is also going to look like a bar graph, but instead of having bars representing how many things there are, you get little pictures. So if you've got 5 people who own dogs, you would have 5 little doggies stacked up. And if there are only 3 with cats, you'd have 3 little cats stacked up. And all of these, though, have to be the same size. So a dog, a cat, they're going to have to be the same size. So that way, a stack of 5 dogs would be as tall as a stack of 5 cats, and that's the part where it's similar to a bar graph, just with pictures. A dot plot is basically sort of a boring pictograph. All those pictures are replaced by dots. So instead of having 5 dogs, you would just have 5 dots in the dog column and 3 dots in the cat column. And again, just like with the pictures, these dots always have to be the exact same size, so that way if it was turned into a bar graph, again, you'd be able to easily compare what you have more of. So a circle graph is going to be a different kind of display. In this case, you're going to have a circle, and it's going to be divided into parts. And so the idea is going to be that each part is set up to represent percentages of a total. So the bigger the section, the bigger percentage. So if something is 50%, then you're going to expect that in the circle, it's going to be half of the circle will represent that part. And again, these are used only when you have a total involved. So if I want to know what percent of students in a class have pets, then I have parts of a total. A line graph is going to be set up somewhat like a bar graph, in that the y-axis is going to represent how tall something is, how many responses you have in that category. But the difference is going to be that the x-axis is going to be dealing with time. And so this is going to show how we use line graphs to show how things change over time. If I want to track student scores over the course of a year, if we want to look at housing prices, if we want to look at a baseball player's batting average over his career, that's going to be something where we would use a line graph. And again, the intervals have to be the same. So when we're talking about time periods, then it would have to be every space represents 1 year or 1 month or maybe 2 months or 3 years, but it has to be a specific and consistent time period. Stem and leaf plots are something that is going to give you an ordered representation of all the data. And again, because it's ordered, this data needs to be numerical. And so you would be taking your numbers and you put them in the stem and leaf plot, and this is the real important part of it. Your stem and leaf plot always needs to be in order. And what happens is then it turns into looking somewhat like a bar graph, and you can see where were most of the numbers. Were they the 20s, the 30s, the 40s, and that. So it's great in terms of that. It kind of is like a pictograph, but it's instead of made out of pictures, it's being made out of numbers. When you went over box and whisker plots, you saw that they're called box and whisker because the basic graph is going to be a box with whiskers on it. And there also is going to be a vertical line somewhere inside the box, and that's going to show where the median is. And that's going to make a difference in things. So this displays the quartiles of the data. And again, remember that a quartile represents 1/4. So from the box and whisker plot, we can't tell how many numbers we're dealing with. But what we will know from it is that 1/4 of all those numbers are going to be in that range. And then the next fourth will be here. And then the next fourth will be here. And then the last fourth are here. So when I look at this just sketch of a box and whisker plot, and again remember that it always will have a scale with it, I look at it and say, wow, that top fourth, the highest numbers, they are really close together. So there's no way there's an outlier up here. This next fourth is also really close together. But then when I look at the bottom half, I see they're kind of spread out. So I see like this quartile here, this fourth of the numbers are pretty spread out. And then this one right here is very spread out compared to the rest. So when I look at this, I could say that there's a very good chance that there's an outlier, 1 or 2 outliers down here that are really extending that whisker out. So they'll have to be the same. So for instance, using something easy, if I was talking about 28 students in a class taking a test, I would know that 1/4 of the students, the top fourth of the students, their scores were very close together, and then the next fourth of students were very close together, and then this fourth of students are spreading out a little bit more. And then I know that my last fourth of students are really spread out even more. And so there's a pretty big difference between my students who are scoring here and my students who are scoring here. Each one of these will represent 7 students. And here, what gets tricky is that I really can't tell. Maybe all 7 were down here. I don't know. Maybe 6 of them were up here, and then there was just 1 student who didn't do their homework. So it's hard to tell, but what it is really good for is showing how the information is concentrated or grouped together. Finally, we have the scatter plot, which is that very different kind of data display, and that's what you did in the previous sections, where you're looking at what's the relationship between 2 sets of information that we get from the same sources. And remember, that was something like looking at a baseball team and looking at what percent of their games they won, and at the same time, how many people were attending their games, and therefore each dot in the coordinate plane represented 1 team, but gave 2 pieces of information about it in order that we could compare those to look for any trends, whether it's positive, negative, possibly nonlinear, where it's curving, or no correlation, and it's all just coincidental. So now let's take a look at a few graphs or a few displays where they're going to sort of misrepresent things. They're going to be entirely correct from a mathematical standpoint, but they're going to give an impression of the data that isn't entirely accurate.